All right, thank you for coming. We'll get started. I think some people took an early spring break, but you guys are here, so thank you for being here. Speaking of that, this will be the last time I'll see most of you for a while, but if you really can't stand to be without me for a week, I will be here most of next week, so we can work something out. I'm suspecting most of you that won't be the case. All right, so we'll get into it, and what we talked about last time, we had just sort of transitioned into Chapter 6, which deals with aqueous solutions and different types of chemical reactions that happen in those solutions. So we talked about how water, being a very polar substance, is able to dissolve other substances, especially ones that are themselves polar or ionic, because we have these interactions between the dipoles in water, the charged ends, the partially charged, partially negative, partially positive ends of water with those other things that are being dissolved. So we can now answer the very important question, if a brown bear and a white bear jumped into the ocean at the same time, which one would dissolve first? Why? All right, good. So the white one would dissolve first because it's polar. So now you guys are happy that you came to class today, and we can actually get into the real stuff, which is talking more about what happens when ionic compounds dissolve. So we're going to start with thinking about more quantitatively the number of ions in solution. And so the first thing to realize is that if we have an ionic compound that dissolves in water, as we talked about last time, it's going to separate into the individual ions. So what this first problem is asking us to think about is, if we dissolve 3 grams of silver nitrate into water, how many moles of ions are present? So we're going to start talking now about moles of individual ions or total moles of ions, as is the case here. So we had to think about what actually happens. If we take solid silver nitrate, so as the picture shows, it looks a lot like table salt. It's a white solid ionic compound. NO3, not in parentheses yet. So the formula for silver nitrate is AgNO3. It's made up of silver 1 cations and nitrate anions. So again, any ionic compound is made up of positive and negative ions. And when we put it into water, so sometimes if you put a substance above an arrow, that just means you're putting it into that substance. So if we put it into water, dissolve it in water, we get the 2 ions separating, silver plus and NO3 minus, and we write them with little AQs next to them to indicate that they are now dissolved in water. So remember that aqueous means dissolved in water. This little symbol AQ next to something indicates that that substance is dissolved in water. And so that's what happens whenever we put an ionic compound in water. It separates into the constituent ions that are now aqueous. And so what we see here is that when we dissolve 1 mole of silver nitrate into water, we get 1 mole of Ag plus and 1 mole of NO3 minus, or a total of 2 moles of ions. So we get, and the number of ions that we get would depend on what the formula of the compound is that we're dissolving. All right, so if we want to answer this question then, and look for how many moles of ions form, if we're starting with 3 grams of silver nitrate, the first step is just going to be a mass to mole conversion of the type that we've done a million times now. So we convert to moles of silver nitrate by using the molar mass. And again, clear labels here are always going to be important, so we know exactly what the quantities mean. So if we divide by the molar mass, which is given as 169.87, that allows us to convert to moles of silver nitrate. But if we again read the question closely, we're looking for moles of ions. So in a separate step, we have to realize that for every 1 mole of silver nitrate, we have 2 moles of ions, 1 each of the positive and negative. So we have to double this. Again, this last step here is one that would often be forgotten by students who just want to, as soon as they get moles, they think they're done. But remember that represents moles of intact silver nitrate. We're looking for the total moles of ions. And so we have to do this last step here to get moles of ions. So it would be 0.0353 mole would be the total number of moles of ions in solution. We could have also done it for one of the individual ions. So if we asked for how many moles of silver plus cations are there, that would just be a 1-to-1 ratio because there's 1 silver plus in the formula. Or if we ask for moles of nitrate, there's only 1 nitrate in the formula. But if we ask for total moles of ions, we have to account for both of them in this case. All right, so any questions on that concept or how we sort of take that additional step for determining ions in solution? Now what we're going to do more often is talk about not necessarily the total number of moles of ions, although that will come up at times, but we're going to talk about sort of a ratio or a concentration unit called molarity. So molarity is what we would call an intrinsic property of a solution. So it doesn't matter about how much solution we have. It's a way of defining how much solute is in that solution, and it's a concentration unit. So the precise definition of molarity, there are several other concentration units that we could use. This is the major one that we're going to encounter in this course, Chem 1332. You introduce at least a couple other ones. But the molarity is basically the moles of solute over the liters of solution. So the units are very important here. It is a volume in the denominator, but it's specifically a volume in liters. And another key point here, at least for knowing the precise definition of molarity, is that we're talking about the volume of solution, not the amount of solvent that we're putting in. All right, so if we wanted to prepare 1 liter of a solution that has a certain molarity, we wouldn't necessarily use 1 liter of solvent. We would use enough solvent to make 1 liter of the solution. And that's because the volume does sometimes change slightly when we dissolve something. The density of the solution changes. So if you put 1 liter of water in to make a solution, it might not be exactly 1 liter after you've mixed the two components together is the point. So it's whatever you need to make the total volume of solution is the important parameter in the denominator. And that's more of a definition thing. It's not going to come up so much in problems that we do, but we do need to know the precise definition. The abbreviation for molarity is just capital M. So as a simple example, if we take 2 moles of solute and make 1 liter of solution, again, enough solvent to make a total volume of 1 liter for the mixed solution, that will be what we would call a 2.0 big M molar solution. So the terminology, we call it a 2.0 molar solution, big M telling us that it's moles per liter, okay? So it's just a ratio of those two, moles and liters. And that's about all there is to it, but we're going to do a lot with it. So it's going to be later on a very important concept as we start doing especially stoichiometry in this chapter with aqueous solutions. All right, so let's go on to another just slightly more complex example. So we want to know, what is the molarity of a solution prepared if we dissolve 15 grams of sulfuric acid in enough water to form 200 milliliters of solution? And again, the terminology there is intentional. It's enough water to form 200 milliliters of solution volume, not 200 milliliters of water, because if you mix sulfuric acid with 200 milliliters of water, you wouldn't know what the final volume of solution is. So again, the terminology there is trying to be precise as possible to make sure we're clear on that definition. This is not what sulfuric acid looks like. This is what sulfuric acid looks like if you put it onto some sort of organic material like paper or cotton, or perhaps your skin. It's pretty nasty stuff. So I don't recommend playing with it, especially in a concentrated form. But anyway, we're just here trying to find the molarity of the solution. So anytime we need to find molarity, if it's not given to us and that's what we're looking for, we have to remember the definition, which is moles of solute divided by liters of solution. So there's going to be 2 parts to this. We're going to need to find both of these terms and then divide them. All right, and so we have enough information to get both, although neither of them are given to us directly. So if we're going to find the moles of solute, the solute in this case is H2SO4. That's what we're dissolving in the water to make the solution. That's our minor component as we talked about last time. So moles of sulfuric acid is just another mass to mole conversion. And we're given the molar mass is 98.1 grams per mole, so we just divide by that. All right, so grams cancels out, and we get 0.153 moles of sulfuric acid. That's the numerator in our molarity calculation. And then we need liters of solution, and this is again where units have to be accounted for carefully. We have 200 milliliters, so we have to convert that to liters, which is dividing by 1,000. So we have 200 milliliters. We want to convert to liters and have milliliters cancel out, and this is just using the prefix milli, which means 1/1000th, or 1 liter is 1,000 milliliters. All right, so we divide by 1,000 to go from milliliters to liters. We will have to do this step a lot in these problems because, or at least keep this in mind, because milliliters is a much more convenient unit for like laboratory scale things. A liter is a relatively big amount of solution to use for like chemistry experiments in a lab. I'm sure when you guys do the chem lab, you don't often use liters of solution, you use milliliters is more common. So we divide the two, then we put the liters up here in the numerator, and what we end up with is 0.765 molar, big M to indicate that it's moles per liter. Okay, so that would be the molarity of that solution. So if we have, something about the solute, its mass in this case, or anything that allows us to convert moles of solute, we just divide that by the volume of the solution to get molarity. All right, one last example that's a little bit more complex, and what we're going to show here is how we're going to often use molarity as a conversion factor, okay? Because it's a ratio unit, it's moles per liter, so we can use it then to convert between volume of solution and number of moles, or vice versa, moles of solute and volume of solution. So in a lot of these problems, we're going to start with one here, and then we're going to see a lot more at the end of chapter 6 when we do stoichiometry again. We're going to use molarity as a conversion factor, as another relationship that involves moles. So we have, we'll see that a little bit more detail later on today. All right, so if we want to look at this problem here, we have a solution of hemoglobin, which is the protein found in red blood cells. We want to know how many heme molecules, so heme being the cofactor in hemoglobin, are there in 25 milliliters of a 0.00150 molar heme solution. So here we were given molarity. We're not going to actually have to calculate it, but we're going to use it to help us solve this problem. So we start by writing out what we're looking for, which is number of heme molecules. And we should recognize that if we're going to find the total number of molecules, Avogadro's number is going to have to be a part of this at some point. But we need moles first before we can use Avogadro's number, because Avogadro's number tells us how many molecules would be in 1 mole. We don't have the moles directly. Remember that this number here does not mean moles, it means moles per liter. So what we're starting with is 25 milliliters of a solution. And we know that there are this many moles per liter. So if we can convert milliliters to liters, we can then use our molarity as a conversion factor. So we can do this in 2 separate steps if we want. We're going to take the milliliters and convert to liters, because molarity, again, is related to liters of solution. So we'll do the same conversion we did last time by dividing by 1,000. And then once we have liters of solution, this is where molarity is very often going to be used as a conversion factor, because again, this big capital M here means moles per liter. So if we want to find out the number of moles of solute that we have, moles in the numerator, in this case the solute is heme or hemoglobin, and we have liters of solution in the denominator, that's going to be written as the molarity, 0.00150 moles of solute for every 1 liter of solution. That's what that is indicating for us with the capital M there. So we use this as a ratio, as a conversion factor. So liters of solution canceled out. Now we have moles of our solute. And then because we're looking for the number of molecules, we have to then multiply by Avogadro's number to figure out how many molecules it is. So 6.022 times 10 to the 23rd molecules of heme for every 1 mole of heme. And when we multiply that across, we get 2.26. Hope that's a 9, because sometimes I can't even read my own writing, which is unfortunate, and probably less fortunate for you guys even. Molecules. I think that's 10 to the 19th should be right for that one. Someone correct me if I'm wrong, but I think that's the right order of magnitude for that. All right, so that's what we get. We get that many molecules. But again, most of these conversions we've done before, it's just adding, we just did a unit conversion at the start, milliliters to liters. At the end, we did Avogadro's number to figure out number of molecules. It's just this intermediate step here, moles per liter, using molarity as a conversion factor to relate how many moles of solute we have in a certain volume of solution. And that's going to come up a lot later on as well. All right, questions on that? All right, so we have a new unit involving moles. Now we're going to see one other thing that we can do with this, which is a concept called dilution. So people in the chemistry industry often joke that dilution is the solution to pollution, which is not a very nice way to think about things, but it is a very important concept in chemistry nonetheless. And again, it comes down to the idea that we have a certain number of moles of solute dissolved in the solution, and then what we're doing in dilution is just changing the volume of that solution by adding pure solvent to it. Okay? So the definition of dilution is we're just adding pure solvent to a solution. Or vice versa, adding a solution to some of the pure solvent. And what we do in this case is make a solution that has a lower concentration, okay? Because we're adding more solvent to the mixture, so the volume of the solution is going to increase. We have the same number of moles, and so moles over liter, that ratio then decreases, okay? So we're going to make a lower concentration of solution. So here's a picture of how this could look. So let's say we have a solution here. Remember, a solution is going to have something dissolved in water. So let's say these little red dots are some solute molecule that's dissolved. And as I've carefully drawn, there are 10 of those solute molecules in this sort of crude example. So we have this first solution here. And then what we do for dilution is we take some larger volume that would include now pure solvent. So we take another sample of just the water, in this case the solvent, and we take this solution and pour the whole thing into here. And when we do that, all of the solute molecules that are in the original solution get transferred to the new larger volume. So we have the same number of solute molecules before and after the dilution. We don't change how many solute molecules we have, because we're taking this whole solution here, dumping it into more solvent. We're changing the volume of the solution, but we have the same number of solute molecules because we're not creating or destroying those in any way. So we still would have 10 molecules of our solute. 5, 6, 7, 8, 9. 10 molecules of solute now in a larger volume, though. So same number of solute molecules, but a larger volume. So if we compare the two, in a sort of relative sense, we have this solution up here that we're starting with has a larger molarity but a smaller volume, and the solution that we end up with has a smaller molarity in a relative sense but a larger volume. Okay? Because again, molarity is moles per liter, so we have the same number of moles in each case. We have a larger volume here after dilution, and so the molarity decreases but the volume increases. Okay? So that's kind of qualitatively what's going on. We should emphasize the point then that the moles of solute stays the same before and after the dilution. Okay? We're not changing how much solute we have, we're just changing how much solvent it's dissolved in. Okay, so that's kind of the concept of dilution. And then the vast majority of what you guys are going to have to do with dilution is be able to use the dilution equation, which we're going to quickly derive right here. It's a pretty simple one. So we're just going to get this relationship, this dilution relationship or equation, we're going to just use the definition of molarity that we've been talking about today. Okay, so big capital M molarity is, as we said, moles of solute divided by volume of solution. And so what that means is if we just rearrange this relationship, rearrange this definition of molarity, molarity times volume is equal to moles of solute. As we said, when you do a dilution, you're not changing the number of moles of solute, so the number of moles of solute you have before dilution initially is going to be equal to the number of moles of solute you have after the dilution, your final number of moles. And so then what that means is the product of M1V1, the molarity and volume that you start with, being the equal to the number of moles, will be equal to the product of the final molarity and the final volume, M2V2. And so this relatively simple equation is the dilution equation, where again the volumes here, to emphasize, V1 and V2 are volumes of solution, not amounts of solvent that we use or anything like that. They're volumes of solution specifically, before and after dilution. Okay? And so if you know the volume before and after, you can determine molarity before and after as well. If you know 3 of those 4 things, you can determine the one unknown. So that's the dilution equation. So anytime you see a problem that says, a solution is diluted or is added, or pure solvent is added to give a final volume of this, all those key words, we should indicate that we're going to use this equation in some way. So let's see a couple of examples of how it's used. So one way would be, let's say we had a solution of sodium hydroxide that was 6 molar, but we wanted to actually make a concentration smaller than that. So we wanted to prepare 250 milliliters of a solution that was instead 0.5 molar. So again, in dilution, you're just changing the concentration of things. So we're going to, as I said, later on in this chapter, we're going to do stoichiometry also, where you're reacting to things, and moles also are important for that. In dilution, you're not actually mixing 2 different things together. You just have the same substance, but it's going to have different concentrations, different molarities before and after the dilution, but it's not changing its identity, it's not doing any sort of chemical reaction as part of that process. So here, it's just an NaOH solution, different molarity before and after, and we want to know what volume is needed to prepare 250 milliliters of the more dilute solution. Okay, so we look at what the problem is asking. The definitions of M1, M2, M2V2 are kind of arbitrary, which one we call which, except that we have to make sure that M and V that are together are paired up. So if we call this initial molarity M1, again, we could have switched these and we'll get the same answer. The final molarity M2, we're preparing 250 milliliters of the 0.5 molar solution. So if 0.5 molar is M2, that means 250 milliliters is V2. So typically in a straightforward dilution problem, 3 of the 4 are given to you. And then what we're solving for is V1, the volume of the first solution that we would have to add in to make the second solution. So we're solving for V1 in this case. M1 V1 equals M2 V2. V1 is equal to M2 times V2 over M1. And one of the nice things about this equation is that the units that we use for volume don't actually matter as long as we're consistent. So we don't necessarily have to use liters, because in this case, whatever units we use for V2 is going to be the units that we calculate for V1. Or if we had solved for one of the molarities and had a ratio of the 2 volumes, V1 over V2, as long as the 2 units are the same, they don't have to necessarily be liters. So in these types of problems, we don't need to convert to liters necessarily, though it's not wrong to do that. It's just an extra step here. So if we solve for V1, we put M2 V2 in the numerator, so the final molarity is 0.5. That's what we're looking for after dilution. The final volume is 250 milliliters. Again, it does not necessarily have to be in liters for this type of problem. And we divide by M1, which is the initial molarity of 6.00. So when we divide these, molarity cancels out, and then we're left with a volume in milliliters, which when we calculate the number is 20.8. So if we take 20.8 milliliters of 6 molar NaOH, add enough water until the volume is 250 milliliters, that new concentration would be 0.5 molar. That's what we were determining here. All right, so any questions on how to use the dilution equation or the concept in general? Okay, so we're good on that. Let's just do one last one that has a little bit more to it. And this one gives us also a bit of an example of how to change concentration units. So like I said, we're not going to do a lot with different concentration units, but in this one we should be able to handle it, because here we're saying that concentrated phosphoric acid is 90% by mass. So mass percent is another way of expressing concentration, meaning that you would have 90 grams of phosphoric acid per 100 grams of solution. So mass percent for a solution is defined very similarly as it is for other contexts we've seen it in. So that's what we're telling you is the concentration for concentrated phosphoric acid, and we have a density of 1.5 grams per milliliter. We want to know how many milliliters of this solution are needed to prepare 2 liters of a 0.1 molar solution. So we should recognize that this is a dilution problem because we're just taking a substance and changing the volume, changing the concentration. So it's just M1V1 equals M2V2 like before. We're again solving for V1. We're looking for how many milliliters of the initial solution do we need to prepare 2 liters of 0.1 molar. So we're going to solve for V1 again, M2V2 over M1. The difference here is that we're given M2, which is our dilute molarity of 0.1. We're given V2, which is 2 liters of that final solution, but we're not directly given M1 in this problem. Okay? So we have to use the information in the first sentence to figure out what our initial molarity is, because the dilution equation only works if our concentration unit is molarity. It wouldn't work if we use other concentration units or try to use 2 different concentration units. That's not going to pan out for us. So we have to convert the initial concentration to molarity. So to do that, we have to remember the definition of molarity. So we're going to try to find M1, and remember that molarity is moles per liter. And so we have to start with the initial concentration unit is mass percent. So as we said, if it's 90% by mass, that means we have 90 grams of phosphoric acid per 100 grams of solution. And what we have to end up doing is converting the numerator into moles of solute, because that's what we need for molarity is moles in the top. And we need to convert the denominator into liters, because that's what we need in the denominator for molarity. So if we convert the numerator to moles and the denominator to liters, we will now have this written as moles per liter, which is molarity. So how do we convert grams of phosphoric acid into moles? That one we should know how to do. Yes, we use the molar mass of phosphoric acid, so grams of anything into moles is just using molar masses, or molecular weight in this case is the appropriate way to say it. So we say that 1 mole of phosphoric acid, H3PO4, I gave you the molar mass is 97.99, so we're going to use that to convert grams into moles. So we've taken care of the numerator and gotten moles of H3PO4 in the numerator, but to find molarity, we need liters in the denominator. Right now we have grams in the denominator. So how do we convert mass into volume? What's the relationship between those two? Someone said it, I think. Density. Yes. So something we didn't really talk a lot about in lecture in class, but it's in the review chapter. So it's a concept we sort of expect you to know. And the relationship between mass and volume is density. Density, again, is expressed typically in grams per milliliter. So if we use the density, we want grams to cancel. So we actually want grams in the numerator in this case to cancel with grams in the denominator. And we want milliliters to be in the denominator. So the density is 1.50 grams per milliliter. So if we put that in here, 1.50 grams for every 1 milliliter, grams cancel out, and now we're in milliliters of solution. And then how do we convert milliliters to liters? Because we need liters in the denominator. We just use the definition of a milliliter, which is 1,000 milliliters per 1 liter. All right, it's a little bit weird here because we're trying to cancel out units that are in the denominator, but so we want milliliters up here to cancel out with milliliters down there, and that leaves us with liters in the denominator. So now we have moles over liters, so when we multiply this out, we get 13.8 molar. All right, so it took a bit of doing, but this is the molarity of concentrated sulfuric acid, which in this problem is our initial molarity, M1. All right, questions on those steps? All right, so then once we have that, we just use the dilution equation to solve for the volume that we need. So we're looking for the volume of that initial solution that we need to prepare 2 liters of 0.1 molar. So we're again solving for V1. So M2 is the final molarity, which is 0.1 molar. V2 is the final volume, which is 2.00 liters. And then the initial molarity, as we just calculated, is 13.8. That was the part we had to go through all those steps to find. So molarity cancels out. In this case, our answer would be in liters, but we have to look closely at the problem and say that we're looking for milliliters. So there's one last step here. This is going to be 0.0145 liters, but then we have to multiply that by 1,000 to get milliliters. So look carefully at units in any problem that you do, especially for these types where Milliliters is most common, but liters can also be involved. So we get 14.5 milliliters in this case. Alternatively, we could have taken this volume, our V2, and converted it to milliliters and put this in as 2,000 milliliters, and that would have given us milliliters directly. So there's a couple ways of getting that, but we do need to make sure that we get to milliliters. And so writing out units will always be important, and so I will encourage you over and over and over and over again to do that. All right, questions on that? All right, we are going to leave numerical problems behind for a while, and we're going to focus on what really is a big part of Chapter 6, which is classifying different types of chemical reactions that happen in solution. So we're going to learn, in many cases, how to predict the products of reactions. So if we take two aqueous reactants and mix them together, figure out what kind of products are formed. We're going to learn how to balance those equations, which in most cases is not difficult, but for the last type takes a little bit of effort and a new strategy for doing that. And then we're going to eventually, at the very end, go back to talking about stoichiometry problems involving these types of reactions. But the first thing we need to do is just learn how to classify the different types of reactions, how to predict reactants and products, and so on. So the first type we're going to talk about is a precipitation reaction. All right, and we actually, in one of the very first day, or maybe the first day of class, we saw a video of this. So if you guys can remember that far back, then we showed a video about conservation of mass where someone mixed two solutions together and weighed them out before and after and saw the mass was the same. And that reaction they were doing was a precipitation reaction. They mixed together two solutions and then some solid formed. In that case, it was a yellow solid. And it's going to be the exact reaction I'm going to talk about here as I introduce these concepts. So the definition of a precipitation reaction is that we mix two solutions together. And for a pure precipitation reaction, if that's all that's happening, sometimes precipitation is combined with acid-base, which is the second type we'll talk about. But in most cases, we'll deal with just pure, straight-up precipitation reactions. So we're going to combine two solutions of ionic compounds, and then one, or in rare cases, more than one, insoluble products forms, okay? All right, so something we have to realize, if it's not already apparent, is that not every ionic compound is able to dissolve in water. So for a precipitation reaction, you're starting with two ionic compounds that are dissolved, that are soluble in water, but then when you mix them together, they form at least one or maybe sometimes two compounds that are not soluble in water, and that they basically fall out of solution and form what's called a precipitate, which would be a solid that then eventually would sink to the bottom of the solution and be able to be collected and separated from the solution, okay? So that's what a precipitation reaction is. So the way that we do these, very often in precipitation reactions, we're going to give you what the two reactants are. We're going to say you mix this ionic compound, that ionic compound, and you have to predict what the products are. So the way we do this is we first think about, at least, or separate explicitly, we're going to separate the reactants into their constituent ions. So as we talked about at the very beginning today, when you dissolve ionic compounds in water, they separate into their individual ions. So the example we're going to work through to get through a lot of these concepts is the one that I showed you on the very first day of class, where what they did was they took potassium iodide, Ki, eventually, there it is, Ki, which would initially be dissolved as an aqueous solution, and they mixed that with lead nitrate, Pb, lead 2 nitrate specifically, which is PbNO3 as an aqueous solution. So the reactants would be these two species as aqueous solutions. And then what we want to think about is when we're trying to decide which products could form, we separate each of these into the ions that make them up. So our potassium iodide is made up of K plus and I minus. So those two ions will be present in solution once that compound is dissolved. And then the other reactant is lead 2 nitrate, so it's going to have Pb2 plus. And then if we're being a little bit careful about stoichiometry, there's two NO3 minuses to balance the charge. What would be two NO3 minuses? Very often we'll just put coefficients in at the end, but we don't want to obviously change the number of ions or change the identity of the compound in the course of doing this. So we figure out what ions are in there, and then to predict the products, typically there's going to be two products that are possible. me just say always two products. I can't think of a time when there's not. So always two products will be possible. So what we do to figure out the two products is we just swap the cations and the anions. So we take the cation from the first reactant, which is K+, and we pair that with the anion from the second reactant, which is NO3-. So we're just swapping cations and anions with each other. So K+ is going to pair with NO3-, so that's going to form KNO3 as one of the products. So just taking cations and anions and flipping them with each other. And then we're going to take the anion from the first reactant, which is I-. We're going to pair it with a cation from the second reactant, which is lead-2+. So if you have lead-2+ and I-, what's the formula for that compound? PbI2 is going to be the second product that forms. We're just taking the cations and anions and swapping them. And remember, when we do this, we don't change the charge of anything. We're not doing any sort of electron transfer or anything like that. That's going to be later on in the last type of reaction we talk about. For precipitation reactions, we're just swapping cations and anions, and they're keeping the exact same charge that they started with. So it's K+ NO3- making one product, Pb2+ with two I- or PbI2 forming the second product. And then what we have to decide to figure out is, which of the products is going to precipitate, if any. So we have to decide whether any of these two products, any of these two combinations of ions, forms an insoluble species. And for that, we have to think about solubility rules, which is one of people, historically one of students' favorite topics in this course. I'm only being slightly sarcastic with that. So we have to think about solubility rules to understand whether or not one or both of these products is insoluble and will, in fact, precipitate from the solution. Okay? We always assume, because we're told that we're starting with aqueous solutions, that the two reactants are soluble, but then in many cases, one or both of the products, usually just one of the two, but sometimes both, will be insoluble and form as a precipitate. And we have to use solubility rules to predict which one of those products that would be. Okay? So if you look at your book, when your book introduces solubility rules, they just give you sort of a long list of rules and just says, here they are, solubility rules, have fun. I like to think about it a little bit more systematically and look for some obvious ones first. Now, some of the rules are a little bit hard to learn, as we'll see at the end of this, but I kind of like to break them down into categories and try to think about them in this exact order that I'm presenting them, because basically this is like a hierarchy. So this rule here, category A, the always soluble category, that's going to reign supreme. So if you ever see one of those ions, you automatically know that the species is soluble and won't form a precipitate, and then you don't have to think about what the other ion is. So we're going to think about these sort of in categories of rules that I think makes it a little bit easier to remember. So when you're looking at compounds to decide whether or not they are soluble, first look for one of the ions that I'm going to put here in what I call category A, which are ones that are always soluble. So if a compound has even one of those ions, whether it's the cation or the anion or both, it will be soluble. You don't have to think about it any more than that. So the cations that fall in this category are mostly just the group 1A cations, okay? Remember, group 1A is the first column of the periodic table, so that would be lithium, sodium, potassium, rubidium, and cesium. And there's one other that falls in this category, which is not on the periodic table because it's a polyatomic, which is NH4 plus ammonium, okay? So that falls into the same category. So if the ionic compound has one of these cations in it, any of these cations as the metal or cationic part of the formula, it will be soluble. It will not form a precipitate in that reaction, okay? And then there's a few anions that also have this same property of always being soluble. So nitrate, NO3-, which is one you'll see a lot in this context. Perchlorate, ClO4-, and then acetate, which we can write either as CH3COO-, or sometimes you'll see it as just C2H3O2. Same thing written two different ways, which we call acetate. These three anions, at least of the ones that we're going to encounter in this course, are ones that you would always assume they're soluble in any ionic compound. So it doesn't matter what the cation is. If it has this anion, it will be a soluble ionic compound. And again, you would not identify that as a precipitate forming in the reaction. So those are the first ones to look for. If you see these ions, you can automatically know that whatever ionic compound they're part of, is a soluble ionic compound and won't form a precipitate in the reaction. Category B, we have some ions that are always insoluble unless they're paired with one of these first ones here, okay? So the cations that fall in this category are silver plus and lead 2 plus. So every ionic compound with silver as the cation, except for silver nitrate, silver perchlorate, silver acetate, any other ionic compound with silver, you would expect it to be insoluble. So this one is almost always insoluble unless it has one of these special anions paired up with it. Same with lead 2 plus. Almost always insoluble unless it's paired up with one of these special anions up here. Okay? The anions that fall in this category, again being anions that almost always form insoluble compounds, are carbonate, CO3 2 minus, phosphate, PO4 3 minus, sulfide, S2 minus, and chromate, CrO4 2 minus. So if the ionic compound has one of these anions in it, it will be insoluble unless the cation is group 1A or ammonium. Any other cation paired with these anions, that compound would be insoluble and it would form a precipitate if it was formed as a product of your reaction. Okay? So those are two categories that I think are very helpful to look for first because it makes it easy to identify potentially which one is or is not the precipitate. Now, the next two categories are a little bit more difficult, so we're going to still have to go through them to be complete. We have a category that I'll label as C. These categories are sort of my doing, so you're not going to see it described this way in the book. But anyway, category C are ions that are usually soluble unless paired with category B. And the only ion that falls in this category are most of the halides. So ionic compounds that have chloride, bromide, iodide as the anion, those are usually soluble unless they're paired with silver or lead. Remember, those are always insoluble in most cases, so those would be insoluble. So the exceptions are, so if they're paired with a category B cation, they would be insoluble. There's two other exceptions we want you to be familiar with. So silver 1 halides are insoluble because that's part of those category B as I called them, but also copper 1, the one right above it on the periodic table. And then mercury, which has a polyatomic cation that's Hg2 with a 2 plus charge, so 2 mercury 1 plus linked together. Those are insoluble halides as well. Those ones don't come up as often. Lead and silver are the two most common insoluble halides that you'll see. But those are two other examples of insoluble halides. But except for lead, silver, copper, mercury, except for those four, every other halide compound you'd expect to be soluble. So all the group 1 halides, all the group 2 halides, calcium, magnesium, all those, many other transition metal halides you would predict would be soluble in this case. And then finally the last one is category D, which I call the in-between annoying ones. These are ones that have probably more exceptions than rules in some sense, but there is still a little bit of a systematic way of learning this. So there's two anions that kind of fall in this category where they're sometimes soluble and sometimes not. The first one is SO4 2 minus. This one is usually soluble, so more often than not it is soluble, but it has a lot of exceptions to that. And so the exceptions are those same cations that we called category B, silver and lead, which pretty much always form insoluble compounds except for a few rare exceptions. So their sulfates are usually soluble except with category B, and they have some exceptions in group 2. So the heavier group 2 cations, calcium, strontium, and barium. So calcium sulfate, strontium sulfate, barium sulfate are insoluble, and then silver and lead sulfate are insoluble. Those are those two cations that are typically always insoluble. The rest of the sulfates are usually soluble, and at least anytime you see it, you would assume that's true. And then the other anion in this category is OH minus. This one, more often than not, is insoluble. However, we have some exceptions as well. So again, there's those category A cations, the cations that are always soluble. So if you have a hydroxide of those, it'll be soluble. So lithium, sodium, potassium, rubidium, cesium hydroxide, those are all soluble because they have that cation in it that's always soluble. But then the other exceptions, actually the exceptions for hydroxide are the same as the exceptions for sulfate. they just go in the other direction. So calcium 2 plus hydroxide, strontium hydroxide, and barium hydroxide, these are soluble in this case. All right, so again, there's not a lot of rhyme or reason to this because we don't know a lot about why these are these different things are soluble and insoluble, but those are exceptions. So sulfate and hydroxide have the same exceptions. It's just that for sulfate, those exceptions are insoluble. For hydroxide, those exceptions are soluble instead. Okay, so it works the opposite direction. So as I said, those are the in-between ones that are a little bit harder to remember, and if you encounter those, it's more difficult to keep them straight. But the vast majority of precipitation reactions, if you understand these first two categories, for a good portion of them, you'll be able to get what you need just from those first two categories. But I, of course, encourage you to learn all of them because they could come up. So again, this is the list given by your book. It's just a seemingly random list of 6 rules, but I think if you put them into those 4 categories and think about them in that order, in that sort of hierarchy, it'll help you a lot when you're doing these problems. Okay? So then once we can identify reactants and products and precipitates in a precipitation type reaction, there's a few different ways that we can write the chemical equation then. All right, so there's, for ionic reactions in general, or for any sort of reaction that occurs in solution, there are 3 ways to write the chemical equation, and we would expect you to be able to do all 3 of these. And depending on the context, sometimes one of them is more useful than the other. So they are, in some cases, more useful than they are in other situations. All right, so the first one, which is called the molecular equation or the formula equation, is the one where we just have the full set of reactants and products, and we don't separate anything into ions. So they're just written as intact compounds. And so all the reactions and products are written intact. We're not separating them into their individual ions in any way. So for the one we've been talking about, we had, as we said, potassium iodide aqueous plus lead nitrate aqueous. And then we said the 2 products that would form are we're going to swap the cations and the anions. So potassium pairs with nitrate to make KNO3. And then lead pairs with iodide to make PbI2. And here we can start thinking about solubility rules to identify whether these 2 species are going to be still dissolved as aqueous ionic compounds or they're going to form a precipitate. So KNO3, potassium is a cation that's always soluble. Nitrate is an anion that's always soluble. So no doubt in our minds that this will remain dissolved as a soluble species. So we still write that as AQ to indicate that it's still dissolved in solution. But if we look at lead iodide, remember that Pb2 plus is one of the cations that's almost always insoluble unless it's with nitrate perchlorate or acetate. So this would form an insoluble precipitate. So we don't write it as AQ anymore because it's not dissolved anymore. We write it as just S for solid. Okay, so whatever our precipitate is in the reaction, if we're writing out the chemical equation, we put an S next to it to indicate that it forms as an insoluble solid. Okay? Now we have some coefficients to put in here as well. These are typically easy to balance because they don't have very large coefficients. So we see that we have 2 iodines on the product side, so we need to have a 2 there. And if we have 2 potassiums and 2 nitrates, we form 2 KNO3. So we do have to have some coefficients to keep this balanced, but they're usually pretty small, 1s, 2s, maybe 3 at the biggest in these types of equations. Okay? So this is balanced, and this indicates then that this is going to be our precipitate. Now the next type of equation we can write, this one is not terribly useful, but we actually kind of need it to be able to go to the last one, which is net ionic. It's called the total ionic equation. So in the total ionic equation, we separate the ions for anything that's a soluble aqueous compound. So separate the soluble ionic compounds. Again, those are the ones that have AQ next to them into their respective ions. All right, and this one takes a lot of space to write out, so I'm going to have to do it kind of small, which is writing small and neat is not my forte, so we'll see how this goes. So what we're going to do is we're going to take all of the aqueous compounds and separate them into ions. So potassium iodide separates into K plus and I minus. They both have coefficients of 2 because we have 2 potassium iodides, so that's going to make 2 K pluses and 2 I minuses if we're trying to keep it balanced. The second aqueous species, our other reactant here, lead nitrate, is also aqueous, so we separate it into ions, which are going to be lead 2+, and then 2 NO3 minuses, because it's NO3 taken twice. So when this dissolves, it makes 2 nitrates, also aqueous. So that's the reactant side. We've separated both of our reactants into their ions for the total ion equation. And then on the product side, we see that our first product here, KNO3, is also aqueous, still dissolved. So we separate that into 2K plus and 2 NO3 minuses. The coefficient of 2 modifies both of those ions. But then we don't separate the lead iodide, because lead iodide here is, again, an insoluble precipitate, so it's not going to separate into ions in solution, so we still keep that as PbI2 solid. All right, so for the total ionic equation, we separate all species that are soluble aqueous compounds into their respective ions. Anything that's insoluble, we still leave it as is. It's still staying together, obviously. Okay? So that's our total ionic equation. And then for the net ionic equation, we just have to remove what are called spectator ions. So if you have ions that appear on both sides of the equation, in some sense they cancel out. They appear as a reactant, they appear as a product. In net, nothing is happening with them, so you cancel them out as what are called spectator ions. So if we look at this total ionic equation, we see that we have 2K plus as a reactant over here, and we also have 2K plus as a product. So those are two of our spectator, or that's one of our spectator ions is K plus, because it appears on both sides of the arrow. There's kind of a math analogy here that could be helpful. So if you have a math equation with a bunch of x's and y's in it, if you have x on both sides of the equal sign, it cancels out. It just subtracts out, right? And same thing in a chemical equation. If you have something that appears on both sides of the arrow, that means nothing is not happening to it, so you can cancel it out. And then our other spectator ion we see is NO3 minus. We have 2 NO3 minus AQ over here. We have 2 NO3 minus AQ over there. So those are our spectator ions. So when we write the net ionic equation, we remove the spectator ions and we leave whatever's left. So we have Pb2 plus. Conventionally, we write cations first, so it doesn't necessarily have to be that way, so don't think that there's anything important about me doing it this way. 2 I minuses are left on the reactant side. And then our product is going to be PbI2. So another way of thinking about the net ionic equation is that it only includes the ions that are combining to make our insoluble product. So it's the lead 2 plus, the 2 I minuses, which combine to make lead iodide. K plus and NO3 minus would be spectator ions, and they would not appear in the net ionic equation. And another reason for wanting to know what are those ions that are always soluble, K plus and NO3 minus being two of the examples of those always soluble category A ions that I introduced, those will pretty much always be spectator ions. They're going to always be aqueous on the reactant side, aqueous on the product side, spectator ions in both cases, in all cases, all right? So questions on that concept of how to write these chemical equations. All right. So, anything? All right, the last thing we're going to cover today then is a couple examples of these, and then we'll do acid-base reactions. So let's get one example of a precipitation reaction, just to take it from start to finish. So we want to write the molecular, total ionic, and net ionic equations. Typically in homework problems, you would identify one of these three, not all three of them. But let's do all three steps of getting these three types of equations for the reaction that occurs between sodium sulfate and silver 1 nitrate. Okay? So it's again silver nitrate, but this time a different reactant that we're pairing it with. So it's typically helpful to start with a molecular equation, and especially in a situation where we wanted to do any sort of stoichiometry with this, the molecular equation is probably the best starting point, because we're going to usually have molarities given for each of the substances separately, and that way you want to think about what they're paired up with at the beginning. So the molecular equation just takes the reactants and products and writes them as intact species. So we have sodium sulfate. We need to be able to take name to formula. So sodium is Na+, sulfate is SO4 2-, and so the correct formula for sodium sulfate then would be Na2SO4. We need 2 sodium cations to balance the 2- charge from the sulfate. So again, don't forget our nomenclature that we learned a while ago. We always sort of assume, if not told otherwise, that our initial reactants are dissolved aqueous compounds. Sodium compounds are always soluble, so we can write that as aqueous. Our second reactant is silver nitrate. We just saw that, AgNO3. Nitrates are always soluble, so we'll put an AQ there as well. And then we have to think about the products. And again, the products of a precipitation reaction, or what's called an ion exchange reaction, is we just take the cation from the first compound and pair it with the anion from the second. So our first cation is sodium plus. Our second anion is NO3 minus. So our first product is going to be sodium nitrate, NaNO3. Those are 2 of our always soluble ions, sodium plus and NO3 minus. So that's going to remain as an aqueous species. And then our second product, we have silver plus 1. This is silver 1 nitrate. And we have SO4 2 minus, so we're going to get Ag2SO4. And is this going to be soluble or insoluble? Okay, yeah, we just saw the rules, so obviously I don't expect you to know all of them now, but silver compounds are almost always insoluble, again, unless the anion is nitrate, perchlorate, or acetate, those 3 exceptions. All right, so we have silver sulfate is our insoluble solid. We need to put some coefficients here, so we have 2 sodiums over here on the reactant side, so we need to form 2 sodium nitrates. Then because we have 2 nitrates and 2 silvers, we also need 2 silver nitrate as well. So again, very small coefficients in most cases, but we do need them to balance the equation. So that's our molecular or formula equation. The next one we can write is the total ionic. And just as we did last time, the way we write a total ionic equation is we separate the species that are aqueous into their constituent ions. So on the reactant side, we have sodium sulfate. So that's going to dissolve to form 2 Na plus and 1 SO4 2 minus. So again, when we dissolve them, the coefficient here tells us how many of each of those ions we have. So it's going to be 2 sodiums and a sulfate, aqueous. Our second reactant, we have 2 silver nitrates. So as we saw last time, if we have 2 silver nitrates, we make 2 Ag plus and 2 NO3 minus. And then on the product side, our first product here is still soluble, aqueous, so we still separate that to 2 Na plus and 2 NO3 minuses. But our second product, silver sulfate, is insoluble, so we don't change anything about that. Okay? So that's going to still have an S next to it to indicate that it forms as a solid. So we don't divide this into ions because it's insoluble. Only the soluble species get divided. And then finally, for the net ionic, we have to cancel out spectator ions. So we see that on both sides of the arrow, we have 2 Na plus over here, 2 Na plus on the product side, so those are spectators. And then the other spectator ion is nitrate, NO3 minus. 2 NO3 minus is there, 2 NO3 minus is there, so it's another spectator ion. And we're left with 2 silver pluses on the reactant side, sulfate SO4 2 minus, combining to form insoluble silver sulfate Ag2SO4 as a solid. All right, so once again, our net ionic equation is just the 2 ions that combine to make our precipitate. All right, last questions on that. All right, so the second category of aqueous reaction, and the last one we're going to cover today, are acid-base reactions. And these actually have some amount of similarity to the ones we just did. We're not really talking about ionic compounds necessarily anymore, but it still is in some sense a swapping of cations and anions in some sense, as we'll see. All right, so first we need to define what acids and bases are and what they look like. We've seen them in the context of nomenclature a little bit, so this won't be completely foreign to us. But an acid there's a few definitions for acid, but the one that we'll use for now is a compound that releases H plus when dissolved in water. So even though hydrogen is a nonmetal, there are a certain subset of compounds called acids where you dissolve the compound and you get in solution what is formerly H+, like what's called a hydronium ion. It's more complicated than that, but we're not going to talk about too many of the details in this course. We just want to talk about the reactions that they do. All right, so that's what the definition of an acid is. So the formula, we've already sort of talked about names and formulas for acids, so this is not entirely new either, is H with some subscript and then X. So X is an anion, so it can be either a monoatomic anion like chloride, bromide, iodide, one of our binary acids, or it can be a polyatomic anion like nitrate, sulfate, and so on. And then N here is the anion's charge. So the acid is going to have however many hydrogens it needs to balance the charge of the anion. Okay? So if it's a 1- anion, it would be paired with 1 hydrogen. If it's a 2- anion, it would be paired with 2 hydrogens, and so on, because remember, it's formerly thought of as H+ in this situation. So it's kind of like, has some analogy to ionic compounds. So that's the formula of what an acid looks like. A base is a compound that releases OH- in water. So hydroxide being the anion that we associate with bases. So most bases, and especially the ones that we'll see in this course, are just metal hydroxide compounds. So they're ionic compounds that have a metal cation paired with hydroxide anion. Remember, hydroxide is OH-, where N is the charge of our cation that they're paired with. So if it's a +1 cation, it would just be 1 hydroxide with that. If it was a +2 cation, it would be the cation with 2 hydroxides, and so on. So just about every base that we're going to deal with has this general formula. It's just an ionic compound with hydroxide as the anion. And when you dissolve that in water, not surprisingly, hydroxide anions get released into water, and that's what we've defined as a base. Okay? There are a lot of other substances that could be classified as bases, but for the most part, we won't talk about those, and you'll see those in Chem 1332 and also later on in organic chemistry as well. All right, so that's a definition of acid and base. Now within these, we have subcategories that are called strong acids, bases, weak acids, bases. And what, like I said, there's a lot of details about the differences between these that we're gonna gloss over, but we do need to know them at least from the context of writing their chemical equations, which ones are strong and weak. So strong acids and strong bases, we saw this a little bit when we talked about electrolyte solutions. These are ones that dissociate completely in water. And as we said last time, that makes them strong electrolytes. So for a strong acid, when you put it into water, it completely falls apart to make H+, and then whatever anion that's paired with, and it completely dissociates into solution. Okay? So the strong acids that we need to be familiar with, there's about 6 of them. It's not too many. So most of the halogen acids, the hydrohalic acids, HCl, HBr, and HI, so those are all group 7 acids, except for HF, all those are strong. Chloride, bromide, iodide are strong acids. And then there's a few that are oxoacids or polyatomic acids that are strong as well. So nitric acid, perchloric acid, and sulfuric acid. Okay, so these are our 6 strong acids, the ones that when we dissolve them into a solution, they're going to completely fall apart into H++ plus the anion, and then they're going to conduct electricity really well because there's a lot of ions in solution. The strong bases are essentially just the soluble hydroxide compounds. Okay? So thinking back to our solubility rules, the bases that would be classified as strong bases because they dissolve in water to release hydroxide would be all of the group 1 hydroxides, lithium, sodium, potassium, rubidium, and cesium. So these are all soluble hydroxides, so they would be classified as strong bases. And then as we also said, most hydroxides are insoluble, but the heavier group 2 hydroxides are exceptions to that. So calcium, strontium, and barium hydroxide are soluble hydroxide compounds that are also categorized as strong bases. All right, so they're just hydroxide ionic compounds. So strong bases are pretty easy to identify because any compound with hydroxide in it, if it dissolves in water, is going to be classified as a strong base. So it's as simple as that. Weak acids and bases do not completely dissociate. Now, this doesn't mean they don't dissolve. It just means they don't fall apart into ions when they do dissolve. So most of the molecules in a weak acid or a weak base remain intact. Weak acids and weak bases is a huge topic in Chem 2, so we're again just going to talk about some of the basics of their chemical reactions, but there's a lot more to it in the next course you'll take. But we just identify some of the common weak acids. Just about every acid that's not listed up here would be classified as weak, but some of the more common ones would be HF, so the other group 7 acid is a weak acid. Phosphoric acid, which is H3PO4. Acetic acid, which can be written as CH3COOH. These are all classic weak acids. And when you put a weak acid into water, it still dissolves. It's not that it doesn't dissolve, but most of the molecules stay together. So if you dissolve HF in water, you mostly just have hydrogen and fluorine still bonded to each other covalently. You get a little bit of H plus and a little bit of F minus that dissociates, so it's still a weak acid, but you don't get the whole thing falling apart. It's mostly still intact HF molecules. Same with these other ones. They mostly stay together in solution. The only weak base that we want you to know about in this course, there's a lot of others, but the only one that we'll see is ammonia, which is NH3. Now, you might be thinking, how the heck is that a weak base? It doesn't have hydroxide in it. So the way that this one works is if you take ammonia and dissolve it in water, it reacts with the water. Some small portion of it does. Again, it's a weak base, so most of the molecules will stay as NH3, but a small portion of them will react with water, and when they react with water, you make ammonium, NH4+, and hydroxide, OH-. So again, if you produce hydroxide in water, that's why it's classified as a base. But this doesn't happen to a large extent. Most of the molecules stay as NH3, so you only get a little bit of OH-, and that's why it's called a weak base. Okay? So these are the weak acids and weak bases that don't completely dissociate in water. So when we talk about acid-base reactions then, in general what's going to be happening is a recombination of H plus and OH minus. So the H plus from the acid and the OH minus from the base combine with each other, and that gives us our net ionic equation. So if we have a strong acid and a strong base reacting with each other, we have H plus from the acid and OH minus from the base, so our net ionic equation is going to be this. H plus from the acid, OH minus from the base. Now can anybody do a little bit of detective work and figure out what do those two make when they come together? H2O, water. Good. And so that is the net ionic equation for every reaction between a strong acid and a strong base. They will have exactly the same net ionic equation, which is H plus OH minus making water H2O. Now, the spectator ions and the coefficients in the overall reaction depend on the identities of the acid and base. Because you can never, again, you can't have H plus by itself. H plus is going to be paired with some anion. And OH minus is not by itself. It's paired with some cation. So you're going to likely have spectator ions or other things happening as well that depend on the identity of the acid and base. And the coefficients as well will depend on that. All right, so then the overall outcome of an acid-base reaction, if we write the whole thing, not just the net ionic equation, is that we have an acid and a base that react with each other. The H plus and the OH minus make water, as we just said. And then the other product of an acid-base reaction, if we're considering everything, is some sort of ionic compound. So the ionic compound is going to be a compound where the cation in that compound comes from the base. And the anion in that compound comes from the acid. So it's whatever's left over when you take the H plus and OH minus, everything that's left over combines to form an ionic compound. In rare cases, that ionic compound would be insoluble, so it's also often possible to have acid-base reactions that include precipitation also. So both things happening at once if the ionic compound that you form is one of our insoluble ionic compounds. Not very often, but it is certainly possible. Okay? So that's the overall outcome. Let's see a few examples then of how these look. And just like precipitation reactions, the coefficients in acid-base reactions are usually pretty small and pretty simple. So if we have nitric acid and potassium hydroxide, we have HNO3. Potassium hydroxide is KOH, two aqueous solutions. And as we said, they combine to form water and ionic compounds. So the H plus and the OH minus make water. We write water as a liquid because that's what it is. We don't write aqueous water. It becomes part of the solvent. And then the ionic compound. So we have K plus from the base is our cation, NO3 minus from the acid combined to make an ionic compound KNO3. And as we've already seen today, this one is a soluble ionic compound, so we just have AQ next to it. It's still in solution. Balancing acid-base reactions is fairly simple, especially on the reactant side, because we can remember that every H plus reacts with one OH minus. So in this case, our acid has one H plus, our base has one OH minus, so they just combine in a one-to-one fashion to make one molecule of water, 1 mole of water. Okay? So it's the number of H pluses and OH minuses have to equal each other on the reactant side. One from here, one from here. They're already balanced. We don't need any coefficients on that side or on the product side. Now that's not always going to be true. So if we have sulfuric acid and potassium hydroxide, sulfuric acid is H2SO4 and potassium hydroxide is KOH. And those combined again form H plus and OH minus make water. So any acid-base reaction you form water as one of your products, and then you form an ionic compound. So we have potassium with sulfate, K plus, SO4, 2 minus, so those combine to make K2SO4, potassium sulfate. Also soluble because potassium is part of the formula. Those are always soluble. But here we do need some coefficients because as we notice, on the reactant side, our acid has two H pluses, so that means we need two OH minuses to react with it. Remember, every H plus reacts with one OH minus. So if we have two H pluses, we need two OH minuses, so that gets a coefficient of 2. And that also means we're forming two waters as a product because it's 2H plus, 2 OH minus to make two waters. You can sort of balance these by inspection as well, but I think it's also helpful to look at the reactant side, figure out how many H pluses your acid has, make sure you have the same number of OH minuses. 2 here from the acid, that means we also need 2 hydroxides from the base. All right? Any questions on those ones? All right, the last one we'll do then, I changed my mind what we're going to do, so you have to edit the problem that's in there. So let's do the net ionic equation for the reaction between phosphoric acid and calcium hydroxide. It's a little bit different than what I initially wrote in there. I initially had acetic acid and barium hydroxide. Let's do phosphoric acid because this one gives us a little bit, a few more things that we haven't seen yet than the other ones. Okay, so this is going to give us a little bit more complex example. All right, so if we're going to write net ionic equations, we can start with the total ionic equation, the total molecular equation. So we have phosphoric acid, which is H3PO4. We have calcium hydroxide, which is calcium CaOH2. All right, and then the products that we form, remember we form water as one of our products. H plus from the acid, OH minus from the base make water. And then we form an ionic compound. So we have calcium 2 plus as our cation. Phosphate is PO4 3 minus. So we're going to get an ionic compound that has the formula Ca3 PO4 2. So that's our ionic compound that forms. But we have a bunch of coefficients in here and some other things to take care of as well. Before we get to coefficients, calcium phosphate, is it soluble or insoluble? I guess I shouldn't ask you that because you just learned it 2 minutes ago. But anyway, phosphate is one of the anions that's almost always insoluble unless it's paired with lithium, sodium, potassium, so on. So this actually forms a solid because this product here is insoluble. So I mentioned it is possible for acid-base reactions to also be accompanied by precipitation, and this is an example. The ionic compound we form is insoluble, so it will fall out of solution. We also have some coefficients to deal with here. So our acid has 3 H pluses, our base has 2 OH minuses. Those have to react 1-to-1 with each other. So how do we take care of that? How do we make sure we have the same number of H plus and the same number of OH minuses? If we had 6 of each, that would work. So we're going to put a coefficient of 2 here, which makes us have 6 H pluses, a coefficient of 3 there to give 6 OH minuses. 2 times 3 hydrogens, H pluses, 3 times 2 is 6 OH minuses. Now we have equal numbers of H plus and OH minuses, so the reactants are balanced. But if we're combining 6 H plus with 6 OH minus, we make 6 waters as a product. So we need a 6 there. That's as big as the coefficients we'll ever get for an acid-base reaction, I promise. And then we're left with calcium phosphate, which is already balanced because we had 3 calciums, 2 phosphates, Ca3PO4 taken twice as our product. Okay? So that's the total equation. And then if we want to split this into ions, we have to think about, again, the ones that we split into ions are soluble ionic compounds and strong acids. So phosphoric acid is actually a weak acid. So when we're writing ionic equations involving acids, the only ones that we split up are going to be strong acids. A weak acid, as we said, mostly stays together in solution, so we don't split that into ions. Calcium hydroxide is soluble, so that could be split into ions. But this is a covalent compound, so we don't split it up into anything. And then this, as we said, is insoluble, so that also does not get split up in the ionic equation. So the only thing that we actually are going to separate into ions is the calcium hydroxide because this is a soluble ionic compound. This is a weak acid, so it doesn't dissociate very much, so we leave it together, and everything else is either a covalent compound or insoluble. So when we write this out, then we get 2H3PO4. We don't split that up because it's a weak acid. This one we split up into 3 calcium 2 plus, and then 6 OH minuses. And then on the product side, we have 6 waters, which we don't split up because it's a covalent compound, and calcium phosphate, which we also don't split up because it's insoluble. All right, and if we look at this, we want to find the net ionic equation. We have to remove spectator ions. Does this have any spectator ions? Anybody see one? I'm going to assume the silence means no, which is correct. So we have calcium 2 plus is an ion on the reactant side, but it does not appear on the product side. OH minus appears on the reactant side as an ion, but does not appear on the product side, so there are no spectator ions in this case. And this is a rare case where the total and net ionic equations are identical because we don't have any spectator ions to remove, so that means the total ionic equation is just the net ionic equation. They're the same thing. So we would just stop here, and if we wanted to get a net ionic equation, that's the best we can do. There are no spectator ions to take out. So the key points on this problem are, if we have weak acids and we're writing an ionic equation, we don't separate the weak acid into ions. Only strong acids would do that. And similarly, if we have insoluble compounds or water formed as a product, those don't get separated either. All right, have a great spring break. If you need anything over the break, if you want to talk to me about anything, I will be around. And I'll see you guys in a little over a week.